All right, well, welcome back, everybody. So I'm going to get going today. I think I figured out the weird thing that was going on with the timing of the slides last time, so hopefully we'll be in better shape here. Plan for the day. Going to do a quick recap of the stuff we covered on Tuesday. We're going to take a little bit closer look at transmission line protection objectives and some of the terminology that we use when we're describing our line protection or protection in general, but primarily related to line protection. And we will just get that last person in. All right, and then we'll start talking about distance protection in a lot more detail. We touched on it briefly last class. And we'll go from there to start talking about step distance schemes, which is a scheme that's applied on, I'd say, probably 90+% very easily, probably 95% or more of transmission lines. Step distance schemes, a very common way of applying transmission protection. And we'll take a look at that scheme and some of the factors that impact the reliability of so yeah, Kia, did you have a question or comment? Okay. So as I mentioned yesterday, jump right in if you get any questions. Raise your hand, flag me down on the video, put your virtual hand up on Teams. Whatever. I'm happy to stop and kind of go over something in more detail. I'll try to make a few pause points in here, but you want this to be interactive, and if you're not understanding something I'm going over, let me know. We can take a look at it from another angle or provide some more context. But yeah, just jump right in and let me know if you have a question on anything. So recap of yesterday. We really did a big picture overview of transmission lines, kind of where they fit into the power system, physical characteristics, electrical characteristics, fault considerations. What are some of the transmission line faults, types of faults we have to look at? So our three-phase, line to line to ground, and single line to ground faults, and how does the electrical system, power system respond electrically to faults? So what are the impacts of the transmission line itself on the voltages and currents that the relays will be able to see at the terminals of the transmission line, where a transmission line could be tens or even 100+ miles long. You're going to have a lot of different variation in what you can expect to see, but you need to cover all of those scenarios with your protection schemes. And we started touching a little bit on line protection, just the basics, protection objectives. What are we trying to do as relay engineers, and how do we describe the reasons why we do things? And kind of quickly ran through some of the typical protection elements. And we're going to go into each of those in a little bit more detail in the next, this class and the next class. But so that's what we covered yesterday. I kind of left it with, if anyone had any questions, we could come back and talk about them today. So any questions or thoughts, anything, wide open for things you might want to talk about before we jump into today's content. All right, sounds like we're good. We'll get going. All right, so this is really another recap from yesterday, but you'll see this slide on almost everything I present if I'm talking about protection, because I think it's really important to be able to frame the decisions we're making as protection engineers in consistent terms and describe and be able to talk through the trade-offs that we provide when we're making a decision. There's a fairly famous book about protection called The Art and Science of Protective Relaying that, it's no one right answer. So you've got to balance a lot of objectives and figure out what you feel is the best solution given a specific application. So this is the terms we'll use to describe that. So reliability is the assurance your protection scheme is going to operate correctly, and that's a balance of dependability and security. One being that dependability being the scheme's going to operate when you want it to for the faults that it's designed to operate for the protected equipment. Security being making sure it doesn't operate when it's not supposed to. So for a non-fault condition or for some other condition, out on the power system, outside of the line itself that you're trying to protect. So that's always a balancing act. As you make something more secure, you're generally making it less dependable. There are some opportunities to get both out of there, but you're going to be sacrificing some of these other things as well. So selectivity is making sure you're tripping off just the failed component of the power system. You're not removing a substation worth of equipment when you could just be tripping off one line. You're not tripping off your line for an adjacent line at the station or one at another substation. Speed is how fast we're able to clear, and that's another good one when we're talking about reliability. The faster you make a tripping decision, the less time, the less information the relay has to make sure it's making the correct decision. So the faster you go, generally, you're going to have some impact on your reliability. Simplicity. So again, that's another method we can go about improving our reliability is by making it more complex. So rather than providing a very simple scheme that might have some reliability issues, you can secure it or improve its dependability and security through adding more logic, more functions, more checks and balances in the scheme. But that comes at the cost of simplicity. So if you make it too complicated, it's going to be hard for people to understand. It's going to be hard for people to upgrade in the future or maintain, which has its own set of problems. Because if people don't understand something, they're more likely to make a mistake when they're working on it. And then lastly, economics. You got to factor in the cost of what you want to do compared to what's available for funding for a project. So throughout the remaining classes and any other time you talk to me in industry, this is the terms we should be using as protection engineers to describe everything we're doing and the reasons why we chose something. We should be able to explain it in these terms. So diving a little bit deeper into protection system objectives and specifically looking at selectivity. So that was basically ensuring that you're removing the smallest amount of the power system as possible for a given fault. So for this simplified system down here, we've got a fault outside the line. So this is shown at station B, but it could be on one of the other transmission lines coming off of this substation. But you've got a fault over here somewhere behind your system. So when we're setting up our relays, either the relay at the local terminal here, station B, or the relay at the other end of the line at station A, we want to make sure we're being selective. We want that protection to operate for a fault along the length of the transmission line up to the boundaries of our protection, which would really be, either considered the breakers or the CTs, which are part of the breakers. And that's really where those relays' responsibility lies, is protecting that equipment. Now, inherently in how we design relay systems, generally they've got some amount of an overreach, or they'll see further into the system past the end of the line. Because if you think about it, how much difference in voltage and current measurement are you going to see for a fault that's, right here? Actually, I'll grab the pointer here. That's right here on one side of the breaker versus right here on the other side of the breaker, if you're measuring them from a location that's miles and miles away. And the answer is not much. There's not going to be a lot of difference in the fault measurements that that remote relay is going to see for those locations. So inherently, we generally design our protection to look past the end of the protected area, but then we need to make sure that it's not going to operate for those faults that are outside of its protected zone. So in this case, you don't want this relay at station A to trip off the line for a fault on some line past station B. Likely your relay will see that fault and will recognize that it is a fault, but you're going to need a way to allow the other protection to operate first. So that's the process of kind of evaluating the selectivity of our protection. And there's two main ways that we go about that. The first is, and kind of this whole process is called coordination, because you're coordinating the timing or the response of one relay with other relays to allow those to clear the fault before you trip for some out of zone area. So the two ways we go about that generally are coordination through sensitivity or coordination through a time delay. So and we'll use a mix of those in protecting a transmission line. So the first, coordination through sensitivity, is selecting your protection set points so that you're going into it with a high level of confidence that the protection will stop operating well before it hits an out of zone area. So you might configure your relay, you find out what the maximum fault currents are for faults towards the end of this line, and you add some margin to that. You add a higher value to that, because as you move a fault down the line closer to station A, the fault magnitudes at station A are increasing. So you might say, okay, well, I'm going to find this fault value and I'm going to add some more margin to it and provide a higher pickup value. And that'll make it so that the relay at station A is going to see the fault only part way down the line. So that's using sensitivity to make sure that your protection is not going to operate for that fault. The downside to just using that is now you've got a portion of this line that your protection is not going to see. It's not going to operate for. So generally we'll pair up coordination using sensitivity with the second method, which is coordination through a time delay. So the approach with that is you allow your relay to see past the end of the line, but for things that you think are going to be past the end of the line, you're going to add a delay to those. And that could be half a second, it could be a third of a second, something on that time frame. And what that time delay does is it allows the protection at station B for this line fault or bus fault or whatever kind of fault is over here. It allows that protection to operate, trip the breakers, isolate the fault, and remove it from the system before the relaying at station A has a chance to operate, because it's still timing and it's waiting to trip its breaker to allow the protection at the other end to do its job. So that's what we do when we're talking about coordination through a time delay. And that's one of the main themes we'll talk about when we're discussing step distance schemes, is you're using a mix of these two approaches to provide faster protection for things are line faults, and you have a high level of confidence they are line faults. And that's using the coordination through sensitivity approach, because you're able to trip very fast when you know there's no chance it's going to be out of zone, or out of the outside of the protective zone. And then you'll provide some other elements that will be coordinating through a time delay, and that'll provide coverage for the rest of the line, but at a slower response because you got to wait for other protection schemes to operate. When we're using time delays, generally we're talking about either a definite time delay. So this is just a timer. The relay sees the fault, starts a timer. When the timer expires to a set amount of time, it'll trip the breakers. The other is an inverse time delay, which you might have covered in some of the other classes or courses here. but it's variable based on the current magnitude. So that would be another way of providing a time delay. And that has the advantage that you can set it up so that higher magnitude currents operate faster, lower magnitude currents operate slower. And as you move down the line, you're moving from higher currents to lower currents. So by the time you get to, this fault, past that bus out of the zone, the current is low enough, maybe it's slow enough at that point. That's the whole process we use to coordinate and validate coordination between the protection schemes in a given area. So a couple more terms and definitions we'll use when we're describing our protection is forward and reverse and overreaching and underreaching elements. So I already kind of hinted a little bit about overreaching elements when I was discussing the protection through time delay and through sensitivity, coordination. But an overreaching element is a line protection element that's set to operate for faults past the remote terminal of the line. So this is one of those that's going to need that time coordination because it's going to operate and it's going to see a fault past the end of the remote station or past the end of the line. So it's going to be able to respond for faults that are out of zone. The other option is an underreaching element. So an underreaching element is configured through that kind of coordination through sensitivity approach that you desensitize it or you make it so it's less sensitive and will stop responding to faults at some point down the line. It could be based on a current or impedance measurement or some other electrical quantity. But you'll evaluate through using tools like Aspen One-Liner to see, what is this relay going to see for faults close to the end of the line. And then you add some margin on top of that to make sure that, the relay is not going to respond to, faults in the last 10, 20, 25% of the line. So those are the terms we're going to use. Really, you can just think overreaching, it's reaching past the end of the station, remote end of the line, past the remote station, and underreaching means it does not protect the whole line. It's only protecting a piece of it because it's underreaching the end of the line. The other terms we use to describe our line protection elements, and almost all line protection schemes use some form of directionality as either a forward or a reverse element. And forward and reverse is in relation to the CTs that the relay is using. And generally, they're configured such that a forward fault is considered a fault on the protected line or the protected equipment. And a reverse fault is something behind it. And again, you're using a directional element of some sort and using the currents and voltages and some reference quantities to determine if the current is flowing onto the line or if it's flowing, out of the line and back onto the system behind the relay location. So you can see here, we've got forward and reverse shown for each of these relay locations. Forward for one relay, the direction of current flow that would be considered forward for one relay is reverse for the other, because the orientation of the CTs are on both ends are looking into the transmission line. So in both cases, a fault on the line itself would be considered forward. Fault, at station B or beyond station B over here would be reverse for the relay at station B, but would be forward for the relay at station A. So we combine these terms quite a bit to talk about and describe how our protection is going to work, and we'll talk about that as we start talking about step distance schemes. So we might say, okay, we're talking about a forward underreaching element or a forward overreaching element or a reverse element. We'd use those to describe the type of protection we're applying. So I'm going to jump in to start talking about distance protection next, but any questions on the terminology or the coordination through time delay or coordination through sensitivity that we talked about already? All right, we are good to go then. All right, so we're going to talk a lot about today about distance protection. It's really the main thing we're going to be talking about today. So a few fundamentals about distance protection. It's IEEE function number 21. So you'll oftentimes see utilities or relay manufacturers use those IEEE function numbers to as shorthand for the type of protection. But you might see a relay applying a 21 element, or a relay at a utility substation being called a 21L relay, or a 21A, or 21S1, or something like that. But that's a way of describing the fact that it's a relay that's primarily using distance protection as its main scheme for what it's doing. Distance protection uses both measured current and voltage to calculate an apparent impedance seen at the relay location. So the relay is using these voltages and currents to determine an impedance that it sees looking out onto the system. And it's called distance protection because it's often set to a certain percentage of the overall line impedance. So the reach, or the operate point of the element, is comparable to a percentage of the length. So if you set your element at 80% of the line, that would be an underreaching element, because it would stop operating at about 80% roughly of the line impedance, which is, assuming your line has a similar impedance per mile or whatever metric throughout the whole thing, because it has a similar build and conductors and things like that. That means that you're going to that element will protect roughly 80% of the length of the line. So again, ties back to that coordination through sensitivity. This would be one of our forward-looking, underreaching elements that would be coordinated through sensitivity. It's not going to operate past the end of the line, so it can operate fast. Because of this approach, you're generally using several elements to provide the full protection of the line. So you're going to need phase elements, ground elements, overreaching elements, underreaching elements. As you get into more complex schemes, you may have forward and reverse elements as well. So I had this on the slide last time, but generally using a mix of phase and ground distance. It's operating on impedance measurement. That's how you set it, though internally in the relay, it's really a comparison of voltage angles with some math that's applied inside the relays. It's just a more convenient way of quickly processing that data and that quantity in the relay. So you're going to need both voltage and current to make that impedance measurement that we'd be using. And we're going to use this in the step distance scheme that we're going to discuss today, but we'll also use it in pilot schemes, which will be one of the topics for tomorrow, for next Tuesday. Generally, your distance elements are going to be directional, so you'll have either forward or reverse elements, and it's going to have separate over and under reaching elements. Forward and reverse elements may be applied. One of the main characteristics between phase distance and ground distance: phase is operating on positive sequence quantities, so will respond for phase faults, but it will also respond to load, because your load current's generally balanced and will have that positive sequence component to it. Ground distance is going to be a primarily zero sequence scheme, so it's only going to operate for ground faults, so single line to ground or phase to ground faults. So because of that, because we don't have a lot of zero sequence component in our loads, it's not going to respond to load conditions. So, when we think back to the security and dependability criteria we may be thinking about in determining our element's reliability, load responsiveness is going to be a really important one, because part of our security criteria is we wanted this to be secure against load. We don't want to have a really hot day and everyone's air conditioner's kicking on at once, and we have a huge load flow through the system, and our line trips off on our protection. So we've got to be really careful for how we set the phase distance elements based on their load. I will talk a little bit about some of the schemes that we can do and some of the tools we have available to handle that. Luckily, ground distance is not responsive to load, which makes that one a little bit easier in that way, but there's some other things that can come into play with that, with mutual coupling considerations and things like that that are unique to ground distance as well. So when we talk about distance protection, one of the ways we describe it is using this kind of RJX impedance plane diagram. So we can take the system and we can take a lot of information about the system and display it on here, because this is basically just a complex impedance plot. So on here, you can see we've got a line here. This represents the line impedance. And you can see the line impedance is closer here to the x-axis than the resistive. And that's because generally you're going to have a line angle, your line impedance angle of somewhere around 80 degrees or so. So that's what's kind of shown here. You've got this line angle, and it's mostly reactive here. When we're looking at this, generally we're looking at a relay location that is at the origin, so at 0, 0 here. So if I'm at this relay, I've got a line in front of me, and then I've got a load. You can model the line impedance itself here. So this is the first station, and this is the remote station of that line. And then we'll be able to dictate on here where a fault is. So if you have a fault on part of the line, chances are going to plot somewhere near the line impedance itself. And that would be the impedance that the relay at this location would see. You could take this and say, okay, that's, whatever, 5 ohms at 80 degrees, or, whatever that value is there. But we can also show on here the load region. Generally, our load of the transmission system or distribution system, really any part of our system, is going to be primarily resistive. And we usually assume something like a plus or minus 30 degree range for a load region. And then we're going to have some amount of maximum loading for the line. So this line may be able to carry 500 MVA of power transfer. And that's going to define this kind of circular region here. And this is, if you plotted it all the way around and didn't have any angle blinders on it, this would continue and it would be a circle around the origin. So this value is your load. So and generally your transmission line load capabilities are determined by the conductors or other equipment. There's some limiting piece of equipment on the transmission line itself, but generally we're talking about the conductors themselves, how much power can that conductor transmit. If you had the same line with the same condition, but you changed out the conductors to ones that could carry more load, this load region would move in towards the origin because the impedance associated with that load would go down. If you have less load, it's going back out here. And you can see we've got a pre-fault value out here in the load region. So you're generally not operating your transmission lines like at 100% capacity. Generally, you're operating them at something much lower than that to give the system some flexibility for future power transfer, power changes, or other lines tripping off, things like that. So your pre-faults plotting out here, your faults over here. So kind of let's think about that. So, I've got a simplified circuit here of the distance relay or impedance relay. We've got our Thevenin equivalent source on the left-hand side of here. Here's our substation bus. Here's the current and voltage measurements. And here's the breaker associated with the line. That's where the CTs would be located. We've got a line impedance, and then we've got the load impedance here. So what the relay is seeing for its apparent impedance measurement based on the voltage and current is going to be the sum of the line impedance and the load impedance. And really in this case, the load impedance is the driving factor. That's going to pull everything way over here. So you're going to, the current associated with the power flow through the line is going to be driven by your system loading. The voltage you're going to be seeing is somewhere near nominal, 1 per unit, maybe plus or minus 5%. And the apparent impedance that the relay will measure is going to be um, relatively large and mostly resistive. So you're way over here, somewhere in this load region, pre-fault. So what happens during a line fault? So we've got the same picture over here, but we're moving from this pre-fault area to the post-fault area. It's the same basic circuit here, but somewhere along this line, about halfway through the line, so where I drew it over here, we have a fault. So, now this is shorting out our system here. And what is the relay seeing now? So now the total circuits still are, they have an equivalent source, got source impedance, and we have some portion of our line impedance. And that's what we're going to be seeing on that phase of the impedance relay is, really just this portion of the line impedance. So the voltage divider between the voltage source and this grounded out fault location is now going to be a voltage divider between this source impedance and the line impedance, or the portion of the line impedance. So because of that, your voltage at your bus is going to decrease and the current is going to increase because you've now drastically changed the impedance between the voltage source and the fault location. You changed the circuit quite a bit. So the apparent impedance the relay is going to see based on that voltage and current, decreased voltage, increase in current, is going to be is going to be proportional to the location within the line. And again, that's why we call it distance protection, is because you can fairly reliably tell where on the line the fault is by looking at the apparent impedance the relay sees compared to the overall line impedance. So, just looking at this, I think I've got a slide on this later, but you can see there's the relay parameter is the same. We're calculating an apparent impedance the relay sees, but the two conditions are very different. We've got a high impedance magnitude at a largely resistive angle for pre-fault, and then during a fault, we shift to a much smaller impedance magnitude at a mostly reactive angle. It's much closer to 90%. So that gives us a really good indication of what is a fault and what is not a fault using distance protection. It's why it's one of the more popular protection methods. Any questions on this before I move on?
Yes, I actually have one. This is Shane. So I see the pre-fault, the X on the screen there in the load region.
Yep.
And I guess I'm not understanding how that ties to the line impedance line that we have for the fault. I see that the fault on that line impedance, that red line in the graph, is about 50% of the way, let's say. So that's,
yep,
to my understanding, is trying to be 50% of the line, like a location.
Yes.
Am I understanding that right? So then maybe the pre-fault X in the load region is that's open-ended. I guess I don't know.
Yeah, so the pre-fault is going to be almost entirely driven by the load impedance, and this is a very simplified version. The math's a lot more complicated when you're talking about a full transmission system with multiple sources and a real two bus having an equivalent system. But largely, when you're talking about the pre-fault, it's the impedance the relay is seeing based on the power flow through the line. And the power flow through the line is going to be determined based on load. But generally, when we're talking about transmission systems, this is a vast oversimplification of what we're doing, because it's usually not a transmission line terminated in a load like this. And if it was, you would have you would have, you'd be able to probably plot out, directly some vectors on here that you could say, okay, line impedance plus load impedance brings me to this point here, or something like that.
Right.
Maybe a bit a better graphic to have for this circuit, but this is an oversimplification. It's really, for that pre-fault, it's not exactly this mathematically. It is just based on the apparent impedance, the voltage and current that it's seeing, due to system loading, the amount of current, power flowing through the transmission line. And that's going to vary because your voltage is going to be right around nominal, and then your current is going to go up and down based on the system load going through the transmission line. But yeah, good point. I think this is probably an oversimplification, and probably could have done a little bit better at drawing the Z load on here to show that pre-fault value, to sketch this out. But great question. Did that kind of answer
Yes.
it?
Yes.
Maybe my figures are a little decoupled from one another. So any other questions? All right. Okay, so we talked a little bit about why impedance is a good metric. We got a good change in or a good operate quantity for our relay. We've got a significant change in both magnitude and angle of the operate quantity that we're going to use for our protection. So that's a good chance we're going to be able to tell the difference between a non-fault load condition and a fault condition. So we'll take a look next at distance protection elements. So on that same RX plane here, we've got our same or very similar line impedance shown up here, and we've added something to it. So we've added this circular shape here, which is our Mo characteristic of the distance protection. So I'll start kind of talking a little bit about the settings and how we configure it. So I mentioned before, we're going to set a reach for the element. Now we're going to have to set a direction. So we got to set if it's forward to reverse. This is going to operate for line faults. It's looking onto the line because you can see it overlaps the line impedance representation on this figure. So this is a forward element is what we're looking at here. The reach determines the sensitivity, how far down the line it reaches. And that's, again, kind of that corollary on distance protection is how far are we looking? And it's based on a percentage of the line impedance. And we're setting it based on secondary ohms in the relay. And the relay will know CT ratios and PT ratios and things like that because you'll configure those. So it'll be able to understand how far to reach. We've got this maximum torque angle. So this basically determines, you could rotate this circle around, leaving one point of it at the origin and then rotate it around to other places on, around this RX diagram by changing this max torque angle. But generally, we're going to always want to have the max torque angle at the line impedance angle, because that's going to give us the most coverage. This is basically drawing a diameter around the circular characteristic, which will determine, more easily where the reach is, and generally we don't have a strong reason to tilt our Mo characteristic in one direction or the other. As kind of a aside on that, the torque angle actually comes from electromechanical relays. Before life was very easy for us protection engineers, a lot of really smart people designed a lot of stuff using electromagnets, electromechanical relays, would, you know, do everything we're doing in the modern microprocessor-based relays, just using magnetic circuits and balance beams and rotating disks and things like that. But back when you used to buy a distance relay, you would have to specify what you wanted your torque angle to be, because instead of being like we can in a modern relay, say, oh, our line impedance is 81.27 degrees, and we plug that in, and that perfectly aligns our Mo characteristic to that value. It used to be you'd have to buy off the shelf of, you know, one of a variety of available torque angles for your distance protection. So you might buy a impedance relay or distance relay that had a torque angle of 75 degrees, and then you'd have to account for the fact that it doesn't perfectly match your line angle when you did the evaluation of how to set up that relay. So the term torque angle in relays is generally, or you know, torque control, things like that. It's generally referring back to the days of electromechanical relays where, you know, everything really did have to do with, you know, magnets and the torque and the, you know, angular forces they were putting on, you know, various components within those. Really interesting stuff. You ever get to play with them, they're kind of it's kind of cool to see that a lot of really smart people figured out how to you know, build something like that. So this is generally what we're going to be talking about when we're setting our relay. We also have a couple others that I didn't touch on here, ground compensation factors. So when we set ground distance elements, we're setting them based on the phase positive sequence line impedance, and then we provide some factors to adjust that. And just makes it a little bit easier to see the relationship between your phase protection and ground protection reaches. And then we'll have some logic. So we'll apply a whole bunch of these different characteristics, elements, but we'll have to combine them, because we're not going to, like I said, we're going to be probably combining, you know, several versions of phase and ground elements, potentially some other stuff for pilot schemes. So we'll need to logically combine those to then provide our overall, you know, trip output. So we'll see a bunch more figures like this as we go. I guess any questions on the general settings? Yeah.
Would you, my name is Kia, would you solve an example in order for us to better understand the, for example, previous diagram or current diagram?
So to show the torque angle and reach, I have some examples further on as we apply this for some other schemes. If we get some time at the end, I will bring up Aspen, and we can take a look at these characteristics for a bunch of different faults on one of the lines. So I think I'll get to that, but if not, just I'm hoping to make it through the last. Wow, I got a lot of slides left, so I'm hoping to make it through the rest of the slides here. If not, we can do a demo of some of this, you know, stuff and what it looks like when you evaluate it in Aspen. I think would be a good way to show that.
Okay, thank you.
Yeah. So if I don't cover it, just let me know. All right. So next, I'm going to start providing some basics on the step distance scheme. So it's a scheme that applies multiple elements, phase or ground. So you typically have a phase step distance and a ground step distance application. And you provide multiple zones to provide that coordination through sensitivity and the coordination through time delay that I mentioned at the beginning of the class. And generally, what we're going to do is call these our protective zones. So the distance scheme is going to have a zone 1, which is our forward-reaching, under-reaching zone. We're going to have zones 2 and 3, which are also forward-reaching, but forward elements, but overreaching, because they're going to see past the end of the transmission line onto the remote bus and beyond. And those are going to have time delays with them. So generally, we're going to use at least zone 1 and zone 2, because that's going to be required to provide protection for the rest of the full transmission line. But occasionally we'll provide a third zone that'll look much further into the system to provide backup in case something fails on one of the other systems off the remote bus. This would be kind of the last ditch effort to try to clear the fault. So we'll go into a little bit more detail on each of those three. So zone 1 is our instantaneous underreaching element. So this is set to trip our local breaker without any intentional delay. So usually it'll take about a cycle, electrical cycle, so 60th of a second for the relay to make a decision and say, is this element within the zone 1 characteristic, or and then it'll trip the breakers immediately. It is set to underreach the remote terminals. So typically we would set this up to look something 70 to 90% of the way down the line. And in some cases, you might need to reduce that a little bit if you've got a real short line application. But generally, this is the protection we want it to operate first. It's going to operate very fast. The more instantaneous coverage we can provide, the better we are, because we're tripping on a very simple scheme and we're able to trip very fast. The further you push it, though, the closer you get to the relay not being able to determine a difference between something just at the boundary of your zone 1 operation and something just past the end of the line. So that's why typically you're not going to see this set to something like 95 or 99%, is because there's not really a lot electrically different in what the relay is seeing for faults that are very close to the terminal versus very, just past it at the remote bus or just beyond. So typical is something around 80%, and that's going to be the first kind of step in our step distance scheme. So next is zone 2, the second step. And this is a time delayed overreaching element. And this element's really just intended to protect that remaining gap that we have between our zone 1 and the end of the line. And that's really its main purpose. It will, by design, we need to set it in a way that we know it is going to operate for any case that could possibly happen in that last 10 to 20% of our line, any fault that happens there. But in doing so, we've got to provide some, margin and have it look past that. Because for the same reason that we don't set the zone 1 to 99 or 100% of the line, you're going to have some variability in what the relay measures, and it's going to have a hard time telling the difference between something that's, right past the end of the line and something that is, just before the end of the line. So we'll provide some margin there. And typically this will be something set to something like 120 to 150% of the protected line impedance. And in doing so, you can make sure that you can make sure and be very confident that that element is going to provide coverage for the entirety of the line in any operating scenario. And we look at this using in feed. So if you have another source, a transformer or a 3-terminal line or something like that, we'll set this up to make sure that, again, we're covering all our bases, and for any possible fault scenario, we know it's going to cover the end of that line. Now, because it's going to overreach the end of the line, we need to make sure we maintain that selectivity. We don't want it to operate for a bus fault. We don't want it to operate for a fault on one of these other lines. So we have to provide a time delay, and that's the selectivity coordination through time delay approach. Because we're going to overreach the remote bus, we've got to provide a time delay. So typically it would be something between a third and a half of a second, 0.3 to 0.5 seconds of delay. And if you get a fault on, let's say, this bus or this line over here, and the relay sees it, you're giving the relays at each of these terminals a chance to trip the breakers before you trip your line off unnecessarily. But we also need to we need to check to make sure that this element doesn't overreach and miscoordinate with any time delayed elements over on these other lines or off the bus as well. So there's some more work we'll have to do there. We'll talk about that a little bit tomorrow. I'm sorry, I keep saying tomorrow, but Tuesday. The last one that we apply is a zone 3. So generally this is applied only on phase protection. We've got some other schemes we'll provide for backup on ground faults. But what this is intended to be is less for a dedicated protection for the line that we're trying to protect, but more for a backup protection for the other lines off the remote bus. So this covers the scenario that, let's say, this breaker fails, or your relay fails and you isn't able to detect the fault on this line. You might need a scheme to cover that. Now, in a lot of modern schemes with utilities who have invested in their transmission system, we don't have to apply this because we've got dedicated breaker failure schemes. We've got redundant protection everywhere. We've got redundant battery systems. We've got redundancy kind of all over in the protection. So it kind of eliminates the need for this type of remote backup protection that reaches. And that's good because this protection has to look very far into the system, which means that it's really opening up a lot of possibility for it to operate when you don't want it to. So generally, we'd be looking at something like, the protected line plus the impedance of another line off that remote bus, or potentially even, a higher impedance to make sure you're covering that scenario. So I'd say it's fairly uncommon on the transmission system to have to apply zone 3. This opens up the possibility of cascading failures because it's very hard to coordinate something that reaches that far into your system. Zone 3 operation was one of the causes of the blackout that happened in the Northeast in the early 2000s. It's so utilities have started moving away from it in favor of dedicated breaker failure schemes and more investment in redundancy, which I think is a good move. So between these 3 schemes, we will start to build a overall protection package for this system. And if we plot all of these, you can kind of see this graphically. So here we are back on our impedance plane. We have our zone 1 element, and you can see that it underreaches the line impedance. We've got our zone 2 element that is larger than the line impedance. And then we've got our zone 3 element, which is very large and is meant to cover the impaired impedance seen for a bus fault at the end of one of those remote lines. And when we start looking at these diagrams, one thing I didn't mention earlier is the operate region for these is any fault or any apparent impedance that the relay sees that falls within the circle will operate that zone. So if there was an impedance where my pointer is, all 3 protective zones would see that fault because it's within all 3 circles. If we move out here, zone 2 and zone 3 would operate for it, but it's outside the boundary of zone 1, so the zone 1 wouldn't operate. And then lastly, we've got this one, this area would just operate for zone 3, and then anything outside of zone 3, the relay is just not going to respond to because it's outside the set criteria that we've provided. One of the other ways we can graphically look at this, so this is a great depiction of why it's called a step distance scheme, is a time distance diagram. So this is showing the relay's response time on the vertical axis here, and the fault location on the horizontal axis. So you can see the phased distance element here from station 1 is shown in red. And for a fault, halfway through this line impedance, you're going to operate instantaneously. Once you hit that 80% mark and go past it, zone one's no longer operating. So the fastest element that's going to respond to this is your zone two element. And you've got looks like a 0.3 second time delay here to cover the remote end of this line, that gap after the zone one stops operating. When you start moving into the next station, one of the lines off the next station, you've got another relay at play here. You've got this station two relay shown in blue. So for a fault, somewhere in the beginning part of this line, for that location, you can see that the relay at station two, the relay that's designed and intended to protect that next transmission line, is going to see that fault in its zone one. And the relay at station one is also going to see the fault within a zone two, but the relay at station two is going to operate faster. That relay is operating within its zone one instantaneously at 0 seconds. So it has this 0.3 second gap here to make a trip decision and open the circuit breakers to clear the fault, plus a whole lot of margin to make sure that before the relay at station one would operate for that condition. And you can see the same thing here as you move down the line and hit let's say the zone two area here. You got your zone two of the relay at station two. That's operating in the 0.3 seconds. But it has plenty of coordinating margin, time margin between the zone two response of the station two relay versus the zone three overreaching zone response of the relay at station one. So it's just another graphical way to show the relationship between protection at one station and protection in the next station. And I think it does a really great job of why this is a step distance scheme, because it's kind of making this staircase approach here. You could plot more of these with more of the system, and you'd see ideally they all stack up like this. What you want to avoid is a condition like this. If, for instance, you're actually, it's going to show up in red, so let's do it this way. If your zone two reached to here, and that line isn't perfectly, well, it'd be operating the same time as this, then you'd have a coordination issue, because in this area, for this fault part way down this line, both the zone two at station two and the zone two at station one are operating the same amount of time, which means both are going to trip. So generally you want to see this coordinating this kind of coordination gap, this time interval between the operation at any fault location on here. And that's something we'd look at and evaluate as protection engineers applying this scheme. Another way that we can use those time distance diagrams is to look at the response of a single line. So we've got our simplified line characteristic here, where we've got the transmission line with the two relays, same one we've been looking at. Well, we can use the same type of diagram to see how the overall clearing of the line is going to look for faults within the line. So in this case, we've got the two relays, one plotted above and one plotted below. So these are both the same relays looking into the same line. And you can see how this step distance scheme provides pretty good coverage for transmission faults. And it's going to do fairly fast clearing. So assuming we had these set at 80% of the line impedance for our zone one, that leaves this last 20% on this end that's going to have time delayed clearing, and 20% on this end that's going to have time delayed clearing from the other terminal. So that means we've got about 60% of the line covered that the relay is going to operate from both ends instantaneously, which means it's going to clear the fault in the matter of a few electrical cycles. You could have a 1 second operate time plus a 3 cycle, or I'm sorry, one cycle operate time plus a 3 cycle breaker clear time. So for faults in this middle area, you might be clearing it in 3 or 4 electrical cycles. For the faults that are closer to the terminals, one end is going to clear instantaneously. So if you get a fault over here by station 2, the station 2 relay is going to operate instantaneously on the zone 1. And the relay from station 1 is going to operate on the time delay. So you will have some delayed clearing, but you're at least clearing one of your terminals instantaneously, which will help reduce the impact of the fault to the power system. So a couple closing thoughts, and then I'll open up for questions, and we can take a look at some of this in Aspen. I think I've got a good case we can kind of take a look at. Some main takeaways here. Impedance is a really strong choice for an operate quantity for line protection, because the impedance, the measured apparent impedance that the relay sees changes quite a bit between normal load conditions and fault conditions. We've got the higher magnitude and more resistive angle for a load condition. We've got a much smaller magnitude and a more reactive angle for fault condition. So that difference makes it a really good choice to be able to differentiate well between different types of faults. Step distance schemes provide the protection for the full line using a mix of the instantaneous and time delayed elements, and the same type of thing would be applied for both phase and ground. And with this type of scheme, one of the trade-offs is that not all the faults are going to be cleared instantaneously, because you have to provide some time, some amount of time delay with a time coordination for your overreaching elements that'll see into the adjacent stations and other protection zones. So we got to wait for that other protection to clear. So with that, before I move over to do a quick demo in Aspen, any questions on the stuff that I covered for the last bit of this, and then
no.
Yeah.
I'm good.
All right, let me see if I can pull up an Aspen model. I think this one I think I have some modeled. Okay, make sure this is. I'm not going to grab that one. That's going to be a. Okay. See, okay. Okay, so no guarantees this protection is going to work well. I'm working on writing a automation program in Python to automate relay settings calculations, and I ran it on this, and it calculated some settings, but I haven't actually looked to see if they're appropriate. So we'll see how they work. So all right, so in Aspen, we're looking at this line between Vermont and Nevada substations. It's a 132 kV transmission line. Apparently it's 0 miles long, but yeah, that's all right. It's got some impedance to it. So it's got, it's a transmission line. On here, you can see we've got, for some basic information, let's see if I can zoom in on this a little bit. Text didn't zoom at all, but all right, well, we'll zoom back out so we can see it. All right, so we've got our line impedance, and then we've got a phase step distance scheme. So we've got a smaller inner Mo characteristic here. That's the circle as our underreaching element. And then we've got a overreaching element here modeled as well. This is our zone 2. So in this case, we didn't provide that zone 3, but we could probably go in and add one if we wanted to. We can go in and add a 5th zone of protection, and we'll put in some big number here. Let's put like 20 ohms and 60 cycles. Okay. All right. So now we've got all three zones of protection here. You will note. Yeah. Okay. You will see here, these are labeled zones 1, 4, and 5. One tricky thing with many relay manufacturers is they have a whole bunch of distance elements, and then they assign certain ones to certain functions. And so this is actually step distance zone 1, 2, and 3, but it's applied using the relay elements 1, 4, and 5. So that's a thing that always confuses folks at first. There's not a direct one-to-one, because the relay could be applying a lot of different schemes with these same elements. So if I go in here and I put faults for every 10% of the line, we're going to put three-phase fault because we're looking at a phase element. And simulate those faults, we can now see the apparent impedance that the relay is seeing. Right away, I can tell that my automatic settings tool did not do a very good job because I've got an in-section fault, and the relay is oh wait, no, okay, no, maybe it's better than it looks because I ran the fault on the wrong line. This relay is at this terminal, so let's try that again. Okay, that looks much better. So this is a fault at 90% of the transmission line. And it is, you can see the fault location, the apparent impedance is mapped here with this box. As I step through and move the fault closer to the relay location, you can see that box moves closer and closer to the relay location until we hit 10% in here. And we could do close-in faults or remote bus faults and stuff like that, but you'll see basically the same thing. So as you move it up the line, you can see it's giving you some information up here in your box. It says that all three units, so the phase-to-phase units, because it is a per phase evaluation as well, zone 1 trip until we hit this 80% mark here, so it's just outside of the protection zone. So it's outside of this smaller zone 1 characteristic, but it's still inside zone 2. And you can see that now it's showing that the zone 4 element's tripped and it's operating in the time delay of 0.5 seconds here. We could also apply some faults. Let's say we add some resistive component to those, and let's put 20 ohms of resistance on there and see what that looks like, and we'll clear those previous results. So you can see by just adding some impedance there, it's moving it further on the resistive axis over here, and the relay is no longer responding to it with just a small amount of resistance added to the fault. It never makes it in there. So resistive reach is something we do look at. It's less of a concern maybe for a three-phase fault like what we've shown here, because it's really hard to just apply a balanced resistance to three energized transmission conductors. Generally, it's more of a concern for ground faults, but you can apply the same kind of approach to any kind of fault here, and do that same thing. So that, I guess, Kia, does that graphically show you more what you were hoping to see with the relationships between the relay response and the faults? Yeah. So we'll probably do a little bit more in Aspen in the next class. I am going to have a homework assignment for you guys. I got to put it together, but I'll have you do some settings calculations. I got an example. I think it's on the next slide deck. It might be the one after that, but it'll be, you know, using Aspen, pulling line parameters like the impedance parameters and things like this out of the software, and you know, then coming up with your own relay settings based on, you know, some typical philosophies and criteria for us applying one of these step distance schemes. So more to come on this next class, but I guess unless there's any other questions, we can probably adjourn, and we'll pick back up here next week.
So can we solve this problem without using Aspen?
Yes, yeah, definitely. So if you just had, you know, from some other software or a hand calculation, we talked about calculating the line impedance last, you know, last class. If you have these parameters, if you have your positive and zero sequence values for R and X, that's what determines this line impedance. So this is in per unit, but you could have it in ohms, primary ohm, secondary ohm per unit. You just got to convert it over. But basically, if you take this R plus JX, that's this impedance here. And then you'd go to set your relay. You know, I don't know what that works out to for an actual, actually, maybe it tells me up here. All right, so yeah, the line impedance is about 8 ohms at 72 degrees roughly. So you could go through and do that same calculation and convert this per unit line impedance into primary ohms, and get a magnitude and angle out of that. And to set your torque angle, you'd use the line angle, the angle you calculated based on those per unit quantities. And then to set your reach, you would take the magnitude times 80%, you know, times for your zone 1 reach, or that magnitude times 120 or 150% for your zone 2 reach. That's how you go about doing it. So most of the time, you know, for these calculations, we're evaluating it in Aspen. We're getting some of our data out of Aspen because that's where it's stored. But the calculations are done, either with Excel calculator, or your hand calculator. You could do them down on paper if you wanted to, which is historically how these have been set. And still are set for most applications.
Thank you.
Yeah. Well, I think our time's just about up. So thanks everybody for hanging in there. And if you get any pressing questions on line protection, definitely let me know for next class. I'll open it up again. We'll do a recap, and I'm happy to answer any questions folks have. So thanks everybody. Have a great rest of your day, and have a great weekend. We'll catch up next week.
May I have your email or something, because there is no email in order to contact you with email or asking.
Yeah, I don't think I have any. Yeah, I don't think I have any yours. Can you see the chat on this?
Yeah.
So I put it in the chat there, and it's also in the slides, which I think Paul sent around to everybody. I sent to him. He said he was going to share them, but it's also on this last slide. So my contact info is there as well. So, but feel free to reach out if you have any questions.
Thanks, Brandon.
All right.
Yeah, thank you, Brandon. Have a good
Thanks.
one.
Have a good one.
Thanks.
Thank you.